Good evening, Pre-Calc. This is lesson 7.5, applications of law of sines and cosines. This would be your day 3 of our lessons dealing with law of sines and cosines. And we've kind of done some of these applications so far. So this is just giving you a little bit more of a directional one and bearings, which are really going to be leading into our next section of vectors. So with that said, we're going to kind of just walk through a couple of examples just to kind of get our bearings on what directional input is and how that applies to law of sines and cosines. So let's kind of dive in here a little bit. So let's just talk about what a bearing is. Bearing in a direction and the information is kind of like what direction is the object traveling at or turning at, and what degrees is that value changing here. So if I give you north 28 degrees east, that means that I'm traveling north first. So if my original line of sight is going to be going straight north, and then I turn at an angle towards the east. So my initial is north, straight north first, and then I'm turning my new angle east, since it's never eat shredded wheat. So we go north first because that's the letter that's represented first, and then we go 28 degrees to the east. That's representing the distance between the north and the new terminal ray. So we have the initial, we have the final ray. The 28 degrees turn is the rotation at which that bearing or that object is rotating at. So it's always first directional, the amount it's turning towards the east or towards the west. So it's always going to be north and south, or it's going to be east and west. Just like if I were to say 28 degrees northeast, it's the same thing as saying that. So if we look at this one down here where we go south 33 degrees west, that means first we're going to be going south. So I'm turning around. My initial view is to look down. And then, since I'm going 23 degrees west, or 33 degrees west, I'm sorry, it's pivoting this line towards the west at a 33 degree angle. Obviously, the angle's not drawn to scale, but we're going towards the west. So it's south here, west this direction. And the angle then goes on the outside. A couple of things we want to keep in mind with both of these is I like to use the example of building your crosshairs. So here's your north, here's your south, here's your east, here's your west. So when I say north 28 degrees east, we know that that value's here based on what I showed you before in the last diagram. But as soon as I put the 28 degrees in there, I actually go down here. Let me switch colors here. I actually go down on both of these and find out what its complementary one would be. So in this case, it would be 62 degrees. So I'm going to put down 62 degrees represents what angle measure would go the other side, or the complementary one, to make it a 90 degree angle. Same thing I'll do here. I'll go 62 degrees. Because as we start putting these images together, we're going to need this 62 to kind of build what the total angle would be. So like down here in this example, when we go south 33, the 33 is going to go on the inside because that's the turn that your revolution or the turn that you're making. And then on the outside, I'm going to go 57 degrees just so I know that, okay, there is my 90 degrees. That is the angle between east to my value instead of south to my value. So it's 57 degrees south of east in that case. So I kind of make sure I like to find its complement every time. So these are going to be the big two things that we're going to kind of get into. The biggest thing with applications is just getting a picture. Trying to interpret what am I looking for. So with that said, let's kind of do an example here. Two planes leaving an airport at the same time. One plane is flying 650 miles per hour at a bearing of north 36 degrees east. So we have one plane, how fast it's traveling at this angle. And then we have a second plane which is flying at 825 miles per hour at a bearing of north, 53 degrees west. So second plane, 825 at a bearing of this. How far apart are the planes after 2 hours? So let's just kind of get a picture here of what's going on. So first of all, we have an airport. So we'll label that A. Plane 1 from the airport is traveling north. So I'm going to kind of draw my crosshairs here. And I'm sitting at the airport. Is traveling north 36 degrees east. So plane 1, and we'll go P1, is ending right here. So we know that it's north 36 degrees east. So I'm going to start at the north value, going to turn towards the east 36 degrees, so that's that inside angle, and then I'm going to find its complement right away. And that complement in this case would be 54 degrees. We might need it, we might not. We'll kind of find out here in a minute. All right, and then that distance represents from A to P is 650 miles per hour. But since we traveled for 2 hours, we need to take this value and multiply it by 2 to represent the distance in miles. So right now, plane 1, or from the airport to plane 1, has traveled 650 times 2 miles. So that would be 1,300. So it's traveled 1,300 miles in 2 hours at a degree or a bearing of north 36 degrees east. Now let's look at plane 2 here. Plane 2 is traveling a little faster, as obviously we see, bearing at a north 53 degrees west. So now this one is going this direction. And we're going to go 53 on the inside because it's north 53 degrees to the west. And that one travels for 825 miles per hour. So we go 825, multiply that by 2, and that's going to give the distance at which plane 2 has traveled. So that would be 1,650, or 1,650 miles at which plane 2 has traveled. So currently we're sitting at a side length, so I'm going to kind of draw another picture here. I'm going to go P2. I'm going to go P1, so plane 2, plane 1, and then I'm going to go airport. I know that this distance here is 1,300, and that this distance is 1,650 because of the calculations that we just made down here. And now the key thing is that this whole angle, ignoring the crosshairs, we now know that this whole angle is equivalent to 53 plus 36. So 59. So 89 degrees. So that angle between plane 1 to the airport to plane 2 is 89 degrees. And I'm asking how far apart are the planes? So how far is it from plane 1 to plane 2 that left the airport at the same exact time? And now looking at what we've done before, we now have our triangle and we're now able to find x. So because we have a side angle side relationship, we're forced to use law of cosines. And since I'm looking for x, x squared is then equal to 1,650 squared plus 1,300 squared minus, oops, let's undo that, plus 1,300 squared minus 2 times 1,650 times 13 . So let's go ahead and erase that. Hands getting a little dirty tonight, I guess. times 1300 cosine of 89. So if we go ahead and solve that, we take 1650 squared plus 1300 squared minus 2 times 1650 times 1300 cosine of 89. And then we take the square root of that value. So after you do all that work and we set this problem up like we just did there, and if you've done the last couple days, now when you solve for x, you get x is equal to 2,182.698 miles apart after that 2 hours. So the only reason I didn't show the in-between step here is because you've been doing them for the past 2 days. So it's a lot of the application is just getting the picture set up. What does it look like? What am I looking for? And then at which angle that things are traveling. Because beyond this now that I know that this distance is 2,082 miles, the follow-up questions I could say is, what angle does plane 2 have to travel at to get to plane 1, knowing that distance? And then it turns into a law of sines question. Alright, so I'm going to go ahead and stop there for this video. This will be part 1, showing you those first 2 examples. So just like I said, reviewing, when we talk about north 36 degrees east and north 53 degrees west, we're talking about making sure we're looking north or south first, and then traveling east or west based on the normal coordinate grid that you've learned for a while. So my advice for all these is set a picture up, set the problem up, see what you have, what am I interpreting, and then apply the law of sines or cosines in any shape or form.